Well, welcome back to our class on discrete mathematics as we look at discrete structures with a focus mostly on computer science. And we're making some good progress as we go through a lot of interesting topics that Rosen has developed for this. And what we're going to be talking about today is focusing on graphs and some of the concepts we've at least to a high level have introduced already, but now we can get really more focused on the material that's related to this chapter. So here are the topics that we're going to cover. There's more things in Rosen that we won't be getting to towards the end of the chapter in Rosen, but anyway, we're going to still be covering a lot of information, graphs and graph models, graph terminology, and types of graphs, representing graphs and graph isomorphisms, connectivity, Euler and Hamiltonian graphs, and those are the things that we'll get a chance to explore. So graphs are discrete structures consisting of vertices and edges that connect these vertices. There are different kinds of graphs depending on whether the edges have directions, whether multiple edges can connect to the same pair of vertices, and whether loops are allowed. Problems in almost every conceivable discipline can be solved using graph models. And so thus graph theory can be quite interesting and useful in a lot of things. We'll give examples to illustrate how graphs are used as models in a variety of areas. For instance, we will show how graphs are used to represent the competition of different species in an ecological niche, how graphs are used to represent who influences whom in an organization, and how graphs are used to represent the outcomes of round-robin tournaments. We'll describe how graphs can be used to model acquaintanceships between people, collaboration between researchers, telephone calls between telephone numbers, and links between websites. We will show how graphs can be used to model roadmaps and assignments of jobs to employees of an organization. Using graph models, we can determine whether it is possible to walk down all the streets in a city without going down a street twice, and we will find the number of colors needed to color the region of a map. Graphs can be used to determine whether a circuit can be implemented as a planar circuit board. We can distinguish between two chemical compounds with the same molecular formula but different structures using graphs. We can determine whether two computers are connected by a communication link using graph models of computer networks. Graphs with weights assigned to the edges can be used to solve problems such as finding the shortest path between two cities in a transportation network. We can also use graphs to schedule exams and assign channels to television stations. This chapter will introduce the basic concepts of graph theory and present many different graph models. To solve the wide variety of problems that can be studied using graphs, we will introduce many different graph algorithms, and we will also study the complexity of these algorithms. So remember, we're trying to do an overview, a survey of this. There is a lot of content here, although the basic ideas are pretty accessible. So let's get into exploring an introduction to graphs, graph taxonomy, and then finally graph models. So in terms of a definition for graphs, a graph, G equals to V comma E, consists of a non-empty set of vertices or nodes and a set of edges. Each edge has either one or two vertices associated with it, called its endpoints, and an edge is said to connect its endpoints. So here's an example that is a graph with 4 vertices and 5 edges. So some remarks that Rosen wants us to be thinking about here. The graphs we study here are unrelated to graphs of functions that we're studying in chapter 2. We have a lot of freedom when we draw a picture of a graph. All that matters is the connections made by the edges, not the particular geometry depicted. For example, the length of the edges, whether edges cross, how vertices are depicted, and so on do not matter. A graph with an infinite vertex set is called an infinite graph. A graph with a finite vertex set is called a finite graph. And so we, following the text, restrict our attention to finite graphs because we can actually show them in a graph form on a view graph or whatever. So some terminology, a simple graph, each edge connects two different vertices and no edges connect the same pair of vertices. Multigraphs may have multiple edges connecting the same two vertices. Where m different edges connect the vertices u and v, we say uv is the edge of multiplicity m. An edge that connects a vertex to itself is called a loop, as we can see there. And a pseudograph may include loops as well as multiple edges connecting to the same pair of vertices. So here is a pseudograph that has multiple edges in a loop, couple loops. And remember, there is no standard terminology for graph theory, so it is critical that you understand the terminology being used, whether you read material about graphs. So a directed graph, now we're going to be showing some directionality. And so it consists of non-empty set V of vertices or nodes and a set E of directed edges or arcs. Each edge is associated with an ordered pair of vertices. The directed edge associated with the ordered pair UV is said to start at U and end at V. And so in terms of remarks, graphs where the endpoints of an edge are not ordered are said to be undirected graphs. So we have this is an undirected graph, and what we're going to be seeing now are directed graphs. So a simple directed graph has no loops and no multiple edges. So here is a directed graph with 3 vertices and 4 edges. A directed multigraph has multiple directed edges where there are m directed edges from the vertices u to the vertex v. We say that uv is an edge of multiplicity m. And so in this directed multigraph, the multiplicity of AB is 1 and the multiplicity of BC is 2. So we can be using graph models. And so this is, say, we're going to be looking at computer networks. When we build a graph model, we use the appropriate type of graph to capture the important features of the application. We illustrate this process using graph models of different types of computer networks. In all these graph models, the vertices represent data centers and the edges represent communication links. To model a computer network where we only connect whether 2 data centers are connected by a communication link, we use a simple graph. This is the appropriate type of graph when we only care whether the 2 data centers are directly linked and all communication links work in both directions. So thus we see that here across the United States, we have a whole bunch of data centers and all have communication links between them. It's not everyone is connected to everyone, but there is a path that we can get connectivity to all of them. So to model a computer network where we care about the number of links between the data centers, we use a multiple graph. So thus now we can see that going, say, between Denver and Chicago, there's a lot of connectivity. And you can see other examples of that as well. To model a computer network with diagnostic links at the data center, we use a pseudograph as loops. And so thus we can be verifying things for each of these centers. And so there's those loops. To model a network with multiple one-way links, we use a directed multigraph. Note that we could use a directed graph without multiple edges if we only care whether there is at least one link from a data center to another data center. So you can see there's examples that sometimes there's more than one link, so you can have more communication flowing in one direction than another. And so that just gives another feature that's in that kind of a graph. So here's a summary of graph terminology. So to understand the structure of a graph and to build a graph model, we ask these questions. Are the edge of the graph directed or directed, or both? If the edges are undirected, are multiple edges present that connect the same pair of vertices? If the edges are directed, are multiple directed edges present? And finally, are loops present? And so thus we have simple graph, multigraph, pseudograph, simple directed graph, directed multigraph, and mixed graph. And so you can be looking over this table, you can pause the video and focus on it, or I would refer you to Rosen to see this summary and get an understanding of everything we've talked about in a summary fashion. So what are applications? Social networks, communication networks, information networks, software design, transportation network, biological networks. And we'll get a chance to explore a little bit of that as they go along, but hopefully this just gives you an idea that there's a lot of stuff that we can be used for. It's a challenge to find a subject to which graph theory has not yet been applied. So can you find an area without application of graph theory? Most likely, at least according to Rosen, that would be pretty tough to do. Okay, social networks. Graphs can be used to model social networks based on different kinds of relation between people or groups. So if you've been on social networking applications, this may be something that you've had some familiar with. So a social network, vertices represent individuals or organization, and edges represent the relationship between them. So its useful graph models of social networks include friendship graphs, collaboration graphs, and influence graphs. And so all are possible things that we can be using. So here is an example of a friendship graph where two people are connected if they are Facebook friends. And so friends of a friend are often things that are used to consider that connectiveness. And finally, we have an influence graph. And so this is something that also could be helpful. Here's another kind. A Hollywood graph models the collaboration of actors in films. And so that would be something that you could consider. An academic collaboration graph models the collaboration of researchers who have jointly written a paper in a particular subject. And so this is something that we could be exploring. And sometimes you have a reference in a paper, and that paper could then reference another paper. And so you could have some interesting collaboration graphs going multiple layers. What about applications to information networks? Graphs can be used to model different types of networks that link different types of information. A web graph, web pages are represented by vertices and links are represented by a directed edge. In a citation network, research papers in a particular discipline are represented by vertices. When a paper cites a second paper as reference, there is an edge from the vertex representing this paper to the vertex representing the second paper. So I'm skipping over some of the details here, but just trying to give you a broad idea of the applicability here. In terms of transportation, graphs are used extensively to study transportation networks. Airline network can be modeled using directed multigraphs, where airports are represented by vertices and each flight is represented by a directed edge. Road networks can be modeled using a graph where vertices represent the intersection and edge represents the roads. Undirected edges represent two-way roads, and a directed edge represents one-way roads. So I'm sure if you've ever looked at a road map, this would be something fairly familiar to you. You can also be using graphs for software design application. Graph models are extensively used in software design, and we can introduce two such models here, one representing the dependence between two models of a software application, the other representing restrictions in the execution of statements in computer programs. When a top-down approach is used to design software, the system is divided into modules, each performing a specific task. We use a module dependency graph to represent the dependency between these modules. These dependencies need to be understood before coding can be done. And here is an example. The dependencies between the 7 modules in the design of a web browser are represented by this model dependency graph. So some of you may end up getting into web design, and so that might be helpful. We can also use it in software design for precedence. And so here we have a precedence graph to represent which statements must have already been executed before we execute each statement. And so this gets into information flow processing. Vertices represent statements in a computer program. There's a directed edge from a vertex to a second vertex if the second vertex cannot be executed before the first. And so thus we can see that we can be looking at that order, and some of this can be utilized for giving optimization of doing threads or different parts of a program. And so those are how that can be useful. And finally, we'll have a couple charts looking at biological applications, an interesting area that some of you may end up having at least part of what you do working in that. Bioinformatics is an example where some of this could flow that deal with computer science, biology, and information technology. So graph models are used extensively to make areas of the biological science. We'll describe here one, two for ecology and the other for molecular biology. Niche overlap graphs model competition between species in an ecosystem, and you can see the relatedness of different animals in an ecosystem, say in a forest or something like that. So here is a niche overlap for a forest ecosystem with 9 species. Some have connectivity with multiple other species, and others it can be fairly lean, like for the mouse in that example. We can model the interaction of proteins in a cell using a protein interaction network. So in these types of graphs, vertices represent proteins, and vertices are connected by an edge of the proteins they represent interact. And you can see some of these have a lot of interactions, some of them not as many. And so this is one of those things that can be helpful for trying to get an assessment of the system function of an organism and how the different proteins relate to each other. Protein interaction graphs can be huge and contain more than 100,000 vertices, each representing a different protein, and over 1 million edges, each representing an interaction between proteins. Protein interaction graphs are often split into smaller graphs called modules, which represent the interaction between proteins involved in a particular function. So you can get a little bit more focused. Okay, well, now let's look at graph terminology and special types of graphs. So this is what we'll talk, basic terminology, some special types of graphs, bipartite graphs. There'll be a couple things that we don't talk about here. And finally, we'll finish up with new graphs from old. So we introduced some of the basic vocabulary of graph theory in this section. You'll use the vocabulary later in the chapter when we solve many different types of problems. One such problem involves determining whether a graph can be drawn in the plane so that no two of its edges cross. Another example is deciding whether there is a one-to-one correspondence between the vertices of the two graphs that produce a graph that produces a one-to-one correspondence between the edges of the graphs. We'll also introduce several important families of graphs often used as examples and in models. Several important applications will be described where these special types of graphs arise. So here are several definitions. I'll just briefly talk about this. And so two vertices U and V in an undirected graph G are called adjacent if G is at the edge E between U and V, such an edge E is called an incident with the vertices U and V. And E is said to connect U and V. Another definition, the set of all neighbors of vertices, as listed here, denoted by N and a V, is called a neighborhood of V. If A is a subset of V, we denote N of A, the set of all vertices in G that are adjacent to at least one vertices in A. So we have this relationship. Finally, a third definition, the degree of a vertice in an undirected graph is the number of edges incident with it, except that a loop at a vertex contributes 2 to the degree of that vertex. The degree of a vertex V is denoted by this notation. Here's an example. What are the degrees and neighborhoods of the vertices in the graph G and H? And so you can be walking through this solution, and we introduce this notation in this last chart, and you can go back and forth between these if you like, just to be tracking what we have here. We also have degrees of vertices. This is called, this theorem is called the handshaking theorem. If G equals to V comma E is an undirected graph with M edges, then we have this relationship that we see here. So we can think about the graph where vertices represent the people of a party and an edge connects two people who have shaken hands. And so this would be why you could be thinking of this as a handshaking theorem. We have a couple examples here we can be thinking about for this. How many edges are there in a graph with 10 vertices of degree 6? And so the number of edges is 30. You can walk through the solution. If a graph has 5 vertices, can each vertice have degree 3? It's not possible is what we get as an answer for that, and feel free to be thinking about that. You can pause the video or look at this up in Rosen. In terms of the degrees of vertices, theorem, an undirected graph has an even number of vertices of odd degree. And so I'm just going to say that's what we have, and you can look through that proof to get some more insight into that. Okay, directed graphs. Recall the definition of directed graph. And so we have that, and a definition, let U of V be an edge in G. Then U is the initial vertex of the edge and is adjacent to V, and V is the terminal or end vertex of the edge and is an adjacent from U. The initial and terminal vertex of a loop are the same. So we're just giving some more terminology here to help us out. The end degree of a vertex denoted by this notation, degree minus V, is the number of edges which terminate at V. The out degree of V denoted by degree plus V is the number of edges with V as the initial vertex. Note that a loop at a vertex contributes 1 to both the end degree and the out degree of the vertex. And so here we can be looking at the details of this graph with the degree minus and degree plus, and you can be looking through those numbers there. Okay, some more things for us to digest here. Theorem 3, let G equals V comma E be a graph with directive edges. Then we have this relationship. So the summation of the degree minus the V is equal to the summation of the degree plus of V. And you can think through the proofs here. I won't walk through that. So here are some special types of simple graphs, and they're complete. And so you have total connectivity between each element in that graph. And that's the definition of complete. And you can be seen as there's more and more elements, it gets to be a lot more lines that we have to draw to make that complete. Another type of special graph, a simple graph, are cycles and wheels. And so here we can be seeing an example of cycles, and below here we can see examples of wheels. And so you can see the cycle, it means that you get back to the initial point. And so each one of these, it goes all the way around. So thus you can think of it as a cycle. A wheel is obtained by adding an additional vertex to a cycle and connecting this new vertex to each of the end vertices by the new edge. So thus there is this center one that helps to increase the connectivity rather than have to go around the whole cycle. Another example is an n-cube, an n-dimensional hypercube, or n-cube is can be use this notation. Qn is a graph with 2 to the n vertices representing all bit strings of length n, where there is an edge between two vertices that differ in exactly one position. So you can see some example here as we move to make it more complicated, and three-dimensional is about the best we can do to be showing that on the way that we're listing it there on that last chart. We can also be thinking of special types of graphs in computer network architecture. Various special graphs play an important role in determining computer networks. How we're going to have connectivity between nodes, for example. So we're going to have a star topology that we're showing that there. We can also have a ring topology, that what we have here in the second illustration. And then we can have a star topology, which is shown there. So various special graphs can play a role in parallel processing, where processors need to be interconnected, as one processor may need the output generated by another. So here we can see an example of 16 processors and the connectedness that we could postulate having between them. Okay, what about bipartite graphs? A simple graph G is bipartite if V can be partitioned into two disjoint subsets, V1 and V2, such that every edge connected a vertex in V1 and a vertex in V2. In other words, there are no edges which connect two vertices in V1 and V2. So it's not hard to show an equivalent definition of a bipartite graph is a graph where it is possible to color the vertices red or blue so that no two adjacent vertices are the same color. So feel free to be thinking about that, and I'll continue on as we go through this. So show that C6 is a bipartite, and so here we can see this is C6, and so we have a cycle, and I'll just let you work through that solution and show that C3 we have here is not a cycle. So there's even number here and an odd number there, which is part of the reason why we get one it is and the other that it's not. We can have complete bipartite graphs, and so it's a graph that its vertex set partitioned into two subsets V1 and V2, such that there is an edge from every vertex in V1 to every vertex in V2. So here are just some examples of complete bipartite graphs. And finally, we can be looking at how we can create new graphs from old. And so in terms of a definition, a subgraph of graph G equals to V of E is a graph W comma F, where W is a subset of V and F is a subset of E. A subgraph H of G is a proper subgraph of H if H is unequal to G. And you can see that literally that you start snipping some of these things away, and you can get something that is just part of what you have in what we've had previous to that. We can be looking at bipartite graphs and matching. They're used to model applications that involve matching the elements of one set to one set to elements in another. So you can be thinking of job assignments or marriage, trying to maybe you're having a dating application. Maybe that would be something that you can be thinking about, or how to assign the best roles to what type of activity, all of them that need to have a mapping. And so this is one of the applications of bipartite graphs. And here's another definition. The union of two simple graphs is a simple graph with vertices v1, u, v2, and edge set e1, u, e2. And so the union of g1 and g2 is denoted by g1, u, g2. And so this is what we can be seeing if we start to click those things together and come up with the end result. Okay, what about representing graphs and graph isomorphism? These are the things that we'll get a chance to talk about. Adjacency list, adjacency matrices, incident matrices, and isomorphism of graphs. So there are many useful ways to represent graphs. As we will see throughout this chapter, in working with a graph, it is helpful to be able to choose its most convenient representation. In this section, we will show how to represent graphs in several different ways. Sometimes two graphs have the same form, in the sense that there's a one-to-one correspondence between their vertices sets that preserves edges. In such a case, we say that the two graphs are isomorphic. Determining whether two graphs are isomorphic is an important problem of graph theory that we'll study in this section. So here we have adjacency, and so we can get directly from one point to another, then they're adjacent, and then we can see what are the lists. And so A is adjacent to B, C, and E to give you an idea. We have a couple examples, and we're showing the adjacency for a simple graph, and then we have an adjacency for a directed graph. And so this is going to be more restrictive because we can't go in both directions for a line when it's directed. So one of the ways that we can represent adjacency is using adjacency matrices. And so these can be interesting. And so this is just a definition of how we can go about laying those matrices out. And so you go from one element to another, and you can be mentioning how many jumps that it takes to go from one to another. So here we're trying to show an adjacency matrix. And so basically, instead of how long it takes, it's just saying if it's connected or not. So this is a simpler form of adjacency. We're not showing the degree of adjacency and going a step further. Now here is where we get into, we can show how far one element is from another. So A, B, C, D. So to go from A to A, it's 0. Go from A to B, there's 3 different ways that we can get there. So that's a lot of connectivity between A and B to give you an idea, and you can see how that looks. Adjacency matrices can also be used to represent directed graphs. So now we have to be thinking about the direction rather than just looking at how connected they are. You can see how this is symmetric because it's undirected. So here is how we create those incident matrices. And so this is the definition, and you can go ahead and pause the video and look over that. Here we see some examples. And so this is just showing the connectivity when we have, this is for a simple graph. And so this is for a pseudograph and incident matrix. So for a simple graph and incident matrix, the rows going from the top to the bottom represent V1 through V5, and the columns go from left to right represent going from E1 to E6. And so for here, the pseudograph and incident map incident matrix. The rows going from top to bottom represent V1 through V5, and the columns going from left to right represent E1 through E8. Okay, in terms of isomorphisms of graph, here is a definition for that. The simple graph G1, V1, E1, and G2, V2, E2 are isomorphic if there is a one-to-one and an onto function f from V1 to V2 with the property that A and B are adjacent in G1 if and only if f of A and f of B are adjacent in G2 for all A and B in V1. Such a function is called isomorphism. Two simple graphs that are not isomorphic are called non-isomorphic. So here is an example, show that the graph G equals VE and H equals WF are isomorphic. And so here we have those two examples here. And so we're just like, you can see the similarities of those, and it's almost like we're just switching the connectivity there, but from one to another so that these cross and this one it doesn't. It is difficult to determine whether two simple graphs are isomorphic using brute force because there are n factorial possible one-to-one correspondence between the vertices set of two simple graphs with n vertices. The best algorithm for determining whether two graphs are isomorphic have exponential worst-case complexity in terms of the number of vertices of the graphs. Sometimes it's not hard to show that two graphs are not isomorphic. We can do so by finding a property preserved by isomorphism that only two of the two graphs have. Such property is called a graph invariant. There are many different useful graph invariants that can be used to distinguish non-isomorphic graphs, such as the number of vertices, the number of edges, and degree sequences. We will encounter others in later sections of this chapter, and we'll just get into a little bit of some of that. So here is an example of isomorphisms in graph. Determine whether these two graphs are isomorphic. So both graphs have 8 vertices and 10 edges. So I'll let you read through this, but ultimately the bottom line is they're not isomorphic. Here's another example. Determine if these two are isomorphic. And if in this case we have G and H are isomorphic graphs. And once again, I'm going to let you can just pause this video or go ahead and even better, spend some time in Rosen and go through that. There's also some more information in Rosen that will help you to be thinking through that. Okay, algorithms for graph isomorphism. The best algorithm known for determining whether two graphs are isomorphic have exponential worst case complexity. So I already mentioned that. Therefore, there are algorithms with linear average case time complexity. You can use a public domain program called NADI to determine in less than a second whether two graphs with as many as 100 vertices are isomorphic. So you can see Rosen for more details about that. Graph isomorphism is a problem of special interest because it is one of the few NP problems not known to not to be either tractable or NP complete. So this is something that we gave a little bit of introduction in chapter 3. So the question whether graphs are isomorphic plays an important role in applications of graph theory. So chemists use molecular graphs to model chemical compounds. Electronic circuits are modeled as graphs in which the vertices represent components and the edges represent connections between them. And so we can see a couple examples here, molecular graphs and electronic circuits where graph theory and graph isomorphisms can be helpful. Okay, what about connectivity? So we're going to be talking about a few things here: paths, connectedness in undirected graphs, connectedness in directed graphs, and counting paths between vertices. And there'll be a few things that we're not going to be covering. So just keep that in mind, and I refer you to Rosen to look at more of those details. So many problems can be modeled with paths formed by traveling along the edges of graphs. For instance, the problem of determining whether a message can be sent between two computers using intermediate links can be studied with a graph model. Problems of efficiently planning routes for mail delivery, garage pickup, diagnostics, and computer networks, and so on, can be solved using models that involve paths and graphs. So paths, an informal definition of path is a sequence of edges that begins at the vertex of a graph and travels from vertex to vertex along the graph. As a path travels along its edges, it visits the vertices along the path, that is, the edge points of these. So this is what you do when you're trying to explore connectivity, and we can see a couple things that we can be thinking about in terms of applications. So here's a definition: let n be a non-negative integer and g be an undirected graph. A path of length n from u to v in g is a sequence of n edges e1 to en of g for which there exists a sequence x0 equal u, x1 all the way up to xn equals to v of vertices such that E has for I equals 1 to n the endpoints x sub I1 and xi. So this is just getting to some of the more detailed ways of thinking about this with a formal way of conjuring up how this all works. So here we can be thinking in a path and a single here for a simple graph. So A, D, C, F, A, D, C, F, and E. Sorry, A, D, then going to C, and then F, and then to E. So I'm not going to put on my thing that I can annotate the charts, but you can be seeing this, and you can see what are paths and what are not. And circuits, you go back to the original origin. And so there's a lot of different things. Even with this relatively simple graph, we can be looking at the various paths that are there. So here's an example, the paths in acquaintanceship graph. And so how well acquainted are individuals? Or if they're not directly acquainted, then they're one removed, two removed, or something like that. Those examples are the kind of things that you can be seeing. The play 6 Degrees of Separation is based on this notion. And so that's another thing that you can be thinking about. Okay, I'm not going to dwell on this, but Erdo's numbers in a collaboration graph, two people, A and B, connected by a path where there is a sequence of people starting with A and ending with B, such that the endpoints of each edge in the path are people who have collaborated. And so this just gives you some information here. There's a link that you can go to. And also, if you go to Rosen, it would be worth the time to read about Erdo's life and what he looked at. Here is another something to consider, Bacon's number. So in the hologram, two actors A and B are linked when there is a chain of actors linking A and B where every two actors adjacent in the chain have acted in the same movie. So sometimes you get people that act together. Maybe they're going to be more likely to have more times that they're going to be doing this. And this, you can see the Bacon number. So kind of like the Erdo number, if you will, but in a completely different setting in different ways that we would see the connections and how they would come up that way. So in terms of connectedness in undirected graphs, an undirected graph is called connected if there is a path between every pair of vertices. An undirected graph that is not connected is called disconnected. We see that we disconnect a graph when we remove vertices or edges or both to produce a disconnected subgraph. So keep that in mind. So, here is an example that you can walk through and see that how that would look like. A connected component of a graph G is connected subgraph of G that is not a proper subgraph of another connected subgraph of G. A graph G that is not connected has two or more connected components that are disjoint and have G as their union. So you can walk through that example just to help you to be thinking about that. Here's a couple of definitions for strongly connected and weakly connected. So strongly connected, if there is a path from A to B and a path from A to B and a path from B to A. A weakly connected is there is a path between every two vertices in the underlying undirected graph, which is the undirected graph obtained by ignoring the direction of the edges of the directed graph. Here is an example. Then we have another definition, the subgraph of a directed graph G that are strongly connected but not contained in larger, strongly connected subgraphs. That is, the maximal strongly connected subgraphs are called the strongly connected components or strong components of G. And there's a couple examples. I'm just going to let you walk through that on your own. The connected components of the web graph. So recall that in any particular instance, the web graph provides a snapshot of the web where vertices represent web pages and edges representing the links. According to a 1999 study, the web graph at the time was over 200 million vertices and over 1.5 billion edges. So as you can imagine, that's just astronomically gotten larger since then, and it will continue to increase, but that would be something that you could be doing with this type of methodology. In terms of counting paths, we can use the adjacency matrix of a graph to find the number of paths between two vertices in the graph. I'll let you go ahead and read through the theorem and think about the proof of that, but I'm just going to move on here. We come back to the adjacency matrix, and so we can be seeing how this all can be of help when we get a chance to be seeing some application here. And you can walk through this example and the solution, but I'm going to move on just to continue with this more of a higher level way of going through this material. Okay, let's talk about Euler and Hamiltonian graphs. So Euler paths and circuits, Hamiltonian paths and circuits, and the applications of Hamilton circuits. Can we travel along the edges of a graph starting at a vertex and returning to it, traversing each edge of the graph exactly once? Similarly, can we travel along the edges of a graph starting at a vertex and return to it while visiting each vertex of the graph exactly once? Although these questions seem to be similar, the first one, which asks whether a graph has a Euler circuit, can be easily answered simply by examining the degree of the vertices of the graph, while the second question, which asks whether a graph has a Hamiltonian circuit, is quite difficult to solve for most graphs. So in this section, we will study these questions and discuss the difficulty of solving them. Although both questions have many practical applications in many different areas, both arose in old puzzles, and we will learn about these old puzzles as well as modern practical applications. And I'm going to try and keep this at a high level. So there was a town in Prussia. It's now part of Russia that was divided into 4 sectors by branches of this Pregel River in the 18th century. 7 bridges connected these regions, and Euler was someone that was able to prove that no such path exists to whether it was possible to follow a path that crosses each bridge exactly once and return to the starting point. So this is this 7 bridges problem that we have here. Okay, here is the definition for a Euler circuit. We have an example that walks through it as well. I already mentioned some of this. A Euler circuit is a graph G, is a simple circuit containing every edge of G, and a Euler path in G is a simple path containing every edge of G. So we have some necessary conditions for Euler circuits and paths. A Euler circuit begins with a vertex A and continues with an edge incident with A, say A comma B, and the edge A comma B continues to degree A. Each time the circuit passes through a vertex, it contributes 2 to the vertex degree. Finally, the circuit terminates when it starts contributing 1 to a degree A. Therefore, degree A must be even. We conclude that the degree of every other edge must also be even. By the same reasoning, we see that the initial vertex and the final vertex of a Euler path have odd degrees where every other vertex has even degree. So a graph where the Euler path has exactly two vertices of odd degree. So in the next slide, we'll show this necessary condition are also sufficient conditions. And I'm going to let you can spend time to go through this, but I'm going to continue to move on just for the sake of time, and this lecture is already getting long. And this continues on. So this is the next slide that helps us to be walking through this reasoning. And so we have a an algorithm for constructing a Euler circuit. So in our proof, we developed this algorithm. And so now we have the pseudocode that we can be using for constructing Euler circuits. So for a computer science application, this is going to be hugely useful. So here is the theorem. Connected multigraph with at least 2 vertices has a Euler circuit if only if each of its vertices has an even degree, and it has a Euler path if and only if it has exactly 2 vertices of odd degree. And so this comes back to this Cronenberg problem that we had a couple of slides ago. So here is another example. I'm going to skip over this for the sake of time. So the application of Euler paths and circuits. Euler paths and circuits can be used to solve many practical problems, such as finding a path or circuit that traverses each street in a neighborhood, road in a transportation network, connection in a utility grid, and link in a communication network. Other applications are layout of circuits, network multicasting, and molecular biology, where Euler paths are used in the sequencing of DNA. Another very interesting area that we'll just have to save for another time, rather than getting into details about that now. Okay, now we have Hamiltonian paths and circuits. So Euler paths and circuits contain every edge only once. Now we look at paths and circuits that contain every vertex exactly once. And so this is going to be harder to try and come up with a way to be showing how this, when this will work, when we get something like that. Here is a definition: a simple path in a graph G that passes through every vertex exactly once is called a Hamiltonian path, and a simple circuit in graph G that passes through every vertex exactly once is called a Hamiltonian circuit. So a Hamiltonian path and a Hamiltonian circuit. So we're defining 2 things there. So here's an example: which of these simple graphs has a Hamiltonian circuit, and if not, a Hamiltonian path. And so you can be walking through that. G1 has a Hamiltonian circuit. G2 does not have a Hamiltonian circuit, but has a Hamiltonian path. And G3 does not have a Hamiltonian circuit or have a Hamiltonian path. So I'll let you be thinking about that, and you can go to Rosen for some more helpful information. In terms of some necessary conditions for Hamiltonian circuits, unlike a Euler circuit, no simple necessary and sufficient conditions are known for existence of a Hamiltonian circuit. There are some useful necessary conditions, and Dirac's theorem and Orr's theorem. And so I recommend that you refer to Rosen and read a little bit about these two individuals to get some perspective on that. And finally, our last chart for this chapter that we're going to cover. So what are the applications of Hamiltonian paths and Hamiltonian circuits? Applications that ask for paths or a circuit that visits every intersection of a city. Each place pipelines intersect in a utility grid, or each node in a communication network exactly once can be solved by finding a Hamiltonian path in the appropriate graph. The famous traveling salesperson problem asks for the shortest route a traveling salesperson should take to visit a set of cities. This problem reduces to finding a Hamiltonian circuit such that the total sum of the weights of the edges is as small as possible. A family of binary codes known as gray codes, which minimizes the effect of transmission errors, corresponds to Hamiltonian circuits in the n cube Qn. Okay, so some things for you to be thinking about that. We talked a little bit about cryptology before. Error correcting codes is a little bit related to that. And now we're getting a chance to see something there where we're extending what we've already spoken about. Okay, thank you very much. That's it for this lecture.